In 1989, a woman in London went to see a dermatologist about a mole on her thigh. She was not worried about it. Her doctor was not worried about it either, at least not at first. She was there because of her dog. The dog was a border collie crossed with a Doberman. For months it had been sniffing at that one spot on her leg. Not the other moles. That one. It would push its nose against her trousers to reach it, through the fabric, again and again. She had moles all over her body. The dog ignored every single one of them except this. Then one day she wore shorts, and the dog tried to bite it off. That is what finally sent her to the clinic. The mole was removed and sent to a lab, and it came back as malignant melanoma, just under 2 millimeters thick, caught early. Still thin enough to treat. Her doctors wrote the case up in the Lancet as a short letter with a question mark in the title. Sniffer dogs in the melanoma clinic? They had no mechanism to offer. No study, no theory. Just a dog that would not stop, and a woman who was still alive. That letter is now treated as the starting gun for an entire field of medicine. And more than 3 decades later, the strangest part is not that dogs can smell disease. It is that in some cases, they are smelling things we still have no machine capable of detecting. Your body is constantly releasing volatile organic compounds. These are small molecules, light enough to lift off your skin and float into the air around you. They come out in your breath, in your sweat, in the oil on your skin. Together they form a chemical cloud that surrounds you all day long, and its composition is not fixed. It shifts with what you eat, how you slept, how hard you have been working, and it shifts when something inside you changes. None of that is controversial. Physicians have known since the time of Hippocrates that certain illnesses change the way a person smells. What is new is the precision. We now know that lung disease, liver dysfunction, kidney failure, and diabetes all leave measurable fingerprints in exhaled breath. The chemistry is real, and much of it has been mapped. The problem is reading it. We have built machines for exactly this. Electronic noses, gas chromatographs, mass spectrometers. They work. But every one of them has a floor, a concentration beneath which it simply stops registering anything at all. For most electronic noses, that floor sits somewhere around 100 parts per billion. A dog's floor is below 1 part per trillion. Sit with that gap for a second, because it is easy to skim past. It is not that dogs are somewhat better than our instruments. Depending on the compound, a dog is working roughly 100,000 times below the threshold where our portable sensors go blank. There is an entire band of chemical information coming off your body right now that our machines record as nothing whatsoever, and that a dog standing next to you is swimming in. For a long time, that was an interesting fact without a use. Then researchers started asking a harder question. Not whether dogs can smell, but whether the thing they would be smelling even exists. Epilepsy was the test case, and on paper it looked hopeless. There are dozens of seizure types with completely different origins. Scarring, genetic conditions, malformations in the brain, old injuries. 2 people with epilepsy might have almost nothing in common neurologically. So why on earth would they produce the same smell? There were stories, of course. There have always been stories. People with epilepsy reporting that their dog, an ordinary pet, never trained for anything, would start behaving strangely before a seizure. Circling, refusing to leave the room, pushing them toward a chair. But stories are not evidence, and nobody could say what those dogs were responding to, or whether they were responding to anything real at all. In 2019, a team led by Amelie Catala at the University of Rennes ran the experiment properly. They collected sweat and breath samples from 5 patients, each with a different form of epilepsy. From every patient, they took a sample during a seizure. Then, crucially, they took controls. 4 samples on ordinary calm days and 2 taken right after exercise. That last set matters far more than it sounds. A seizure involves violent movement and physical stress. If a dog were simply alerting to the smell of someone exerting themselves, the whole result would collapse. Those exercise samples were built into the design to make the test fail if it deserved to fail. The samples were frozen, shipped from France to Indiana, and presented to 5 dogs from a training organization called Medical Mutts. All of them rescues. All of them mixed breeds. None of them had ever encountered any of these people. 7 sealed cans arranged in a semicircle. One of them held a seizure sample. Every dog found it, every single time. 3 of the 5 performed at 100%, perfect sensitivity and perfect specificity. The other 2, newer to the training, still landed at 67% sensitivity and 95% specificity. Chance alone would have given them 14. Average time to a decision was around 9 seconds. And they did it on the very first trial, before there was any opportunity to learn from the samples sitting in front of them. When the researchers measured how long each dog spent investigating each can, the seizure sample drew about 5 seconds of attention. Everything else drew well under 1. So there is a seizure smell. It is shared across people whose epilepsy has nothing else in common. That was the finding, and nobody had ever shown it before. Here is what the study did not show, and the researchers were direct about this. Every seizure sample was collected during the event or within a few minutes of it, not before. The experiment proves that a seizure has an odor. It does not prove that a dog can smell one coming. Those are two different claims, and the second one is still open. Which brings us to the disease where all of this gets genuinely strange. Joy Milne is a retired nurse in Scotland. Years before her husband was diagnosed with Parkinson's disease, she noticed that he had started to smell different. Not unpleasant exactly. Musky was the word she used. She mentioned it. Nobody thought much of it. He was diagnosed at 45. It was only much later, sitting in a room full of other Parkinson's patients, that she realized the smell had never been her husband's at all. It belonged to the disease. Parkinson's changes the sebum on your skin, the oil your glands produce. Patients often develop noticeably waxy or oily skin, and that change appears to begin early. The word early is carrying enormous weight in that sentence. There is currently no single reliable test for Parkinson's disease. No blood panel that settles it. No scan that closes the question. Diagnosis is made by watching for symptoms, and by the time those symptoms are visible and persistent enough to name with confidence, the underlying process may have been running for a very long time. Researchers working on this put that window at up to 2 decades. In 2025, a team from Bristol, Manchester, and the charity Medical Detection Dogs published what happened when they trained dogs on it. They started with 5. 3 of them washed out. The 2 that finished, a golden retriever named Bumper and a black Labrador named Peanut, trained on more than 200 sebum swabs and were then tested double-blind on 100 swabs they had never encountered. Bumper and Peanut correctly identified 70 and 80% of the Parkinson's samples. They correctly ignored 90 and 98% of the controls. And they held up on samples from patients who had other health conditions layered on top of the Parkinson's, which is exactly the kind of messy real-world noise that usually wrecks a test like this. 2 dogs, a disease with no early test, detected from the oil on someone's skin. At which point the obvious question is why we do not simply find the compound and build a sensor for it and skip the dog entirely. That is exactly what researchers have been trying to do. It is proving much harder than anyone expected. The reason appears to be that there may not be a compound, not a single one. The best current thinking is that what a dog recognizes is not one molecule sitting above a threshold, but a pattern, a particular ratio between dozens of compounds, most of which are individually unremarkable, and all of which are also present in perfectly healthy people. The signal is in the proportions. A machine built to look for a specific marker will walk straight past that. You cannot detect a chord by listening for a single note, and a dog's nose is not really a detector in the way we build detectors. It is a pattern recognition system that happens to run on chemistry, shaped by tens of thousands of years of needing to know who came through here, how long ago, and what state they were in. So the machines are not failing at sensitivity alone, they are failing at the question. Now for the part that tends to get left out and should not. The gap between what dogs do in a controlled room and what they do in a living room is large, and it does not run in the dog's favor. Diabetes alert dogs are the clearest example because they have been studied the hardest. When accuracy is measured from the owner's own records, the numbers look excellent. One study of 27 trained dogs across roughly 4,000 out-of-range episodes found median sensitivity to low blood sugar above 80%. But when a separate team took the owner out of the measurement entirely, using continuous glucose monitors alongside CCTV footage, sensitivity to low blood sugar came out closer to 56%. For high blood sugar, closer to 36%. Both sets of numbers are real. The difference between them is mostly a question of who was holding the clipboard. Cancer detection scatters even harder. In one review, dogs detecting breast cancer from exhaled breath reached 88% sensitivity, while dogs detecting the same disease from urine samples came in at 22%. Prostate cancer results range from 18% in one trial to near perfect in another. That spread is not really dogs being unreliable. It is a young field still arguing about how to collect a sample, how to train an animal, and what counts as a fair test. And your dog specifically? Almost certainly has not been trained for any of this. The pet dogs in those famous anecdotes, the border collie, the Labrador that would not leave a patch of skin alone, were not detecting disease in any meaningful sense. They were noticing that something about their person had changed, and reacting to the strangeness of it. Sometimes that turns out to matter. Sometimes a dog just likes licking your ankle. So if your dog fixates on one particular spot on your body, week after week, in a way it never did before, that is worth mentioning to a doctor. It is not a diagnosis. It is a reason to get looked at, in exactly the way the woman in 1989 got looked at. The value was never in the dog understanding what it had found. It was in her going. What stays with me here is not the accuracy figures. It is the ordinariness of it. Your dog is not scanning you. There is no diagnostic intent behind those eyes. It is simply that the information is there, lifting off your skin, riding out on your breath, and their nose is built to a resolution that reaches it. They are not looking for anything. They just cannot help receiving it. Which means that on some level, your dog has always known more about the state of your body than you do. Not in a mystical way, in a chemical one. The seizure that has not started yet may already have a smell. The disease that will not be diagnosed for another decade may already be changing the oil on your skin. We built machines to reach down into that band of information, and so far they cannot quite get there. The animal asleep at the end of your bed has been living in it the whole time,